So hello and welcome to this complimentary webinar. My name is Lennart Eriksson and I'm part of the data analytics team of Sartorius Stedim. Today we're going to have presentation number 10 out of 11 in a series of webinar aimed at discovering the geometric suite of data analytics solutions. The subtitle of today's presentation is Automatic Optimization with Supervisory Process Control, and the presenter is the lead data scientist, Chris McCready. And what he doesn't know about multivariate data analysis is probably not worth knowing. So Chris, please, the word is yours.
Thank you, Leonard, for the kind introduction. Yeah, so what I will be speaking today is some of the, I guess I used to say new offerings in SIMCA-online, but now it's been a few years. So these are not so new and fresh anymore, but still maybe new to many of our existing SIMCA-online users, and obviously new to those who are not SIMCA-online users. To begin, I will though first say a few words of where this fits in terms of the whole set of offerings from Umetrics, and even later on put in context of Sartorius, as we are now part of the Sartorius group. But if you look at the Umetrics suite, as we call it, which is a collection of tools, we have MODI, which is design of experiment to create data for modeling. We have Easy Analytics, which is sort of a data visualizer for non-multivariate users. We have SIMCA, and this is the heart of most of our data analytics, whether it be just some simple desktop analysis or whether it be to do a full-fledged supervisory control. It all starts with SIMCA, with the modeling. And from there, if we do good things and build nice models in SIMCA, we can move to to get these to run in our manufacturing environments in real time with SIMCA-online. And if we have the right type of models, perhaps we can have SIMCA-online and these models to direct us in how we should run the process with Control Advisor. And this is what I'll really be focused on today, is the Control Advisor aspects. And then we have at the very top, we have a visualizer enterprise, you can say, visualization of all processes running and how they're running throughout an enterprise. That's Active Dashboard. So in terms of the content of today, I'll talk a little bit of what do I mean by certain terminologies like predictive monitoring, optimization, advanced control, and model predictive control, and explain what does that mean in terms of the SIMCA-online environment. I'll talk in SIMCA-online then what are the features in Control Advisor, and this is the supervisory control that's in SIMCA-online. And there are two modes of operation, forecast and advise future. We'll talk what those mean. Talk how do we get these predictions of the future? So how are we able to do forecasting? And then how can we use those forecasts to do optimization and build a model predictive control? And then finally, I'll end with a demonstration. So if you take the typical monitoring type of application, and 10 years ago this was bleeding edge technology. Now this is barely even leading edge. This is now just the way that many of our let's say customers. So in biologics manufacturing, this is now the accepted way to monitor processes, which is that you characterize and build models of your process, multivariate models of your process, and then track that are these, as the process is running, are you following this multivariate type of trend? So what we're looking at here is a score control chart. And the monitoring aspect then is, the goal is to detect and diagnose issues as they happen. So if there's something that will happen in the future, we of course don't know that yet. All we can do is look at what's happened up to the current time point. Predictive monitoring or forecasting is to then say, can we, based on the way the process has run so far, can we forecast or are we able to predict where the process is likely to go? And again, if I use biologics as the base point or the reference, in cell culture, often or almost always, you can very early on, the cells give you indication of what their performance is. So if we can look at how the process is running in the first day or two, if it's a, let's say, 14-day cycle, we can, more often than not, we can forecast then how the rest of that run is likely to go and what the final titers, final yields, final qualities will look like. If we have the ability to steer the process, so we have some, like we could change nutrient feed, or we could change DO or pH or some other type of factors, then perhaps what we can do then is we can use these predictions inside of an optimization methodology to say, well, how should we best set the nutrient feed or the glucose profile or the whatever, the DO and pH. How best should we set those so that we get a better result, an optimized result? And that then is model predictive control. And in SIMCA-online, this is called advised future. So the goal here then is to detect and mitigate deviations before they happen. So the question might be, how do we get these predictions? It seems sort of magical how we can get these, but it's actually somewhat simple, hard, let's say, to implement and hard to really get all the details, but philosophically it's quite simple how it's done. If we take a simple example like two variables here, and if we plot them, we see that there's correlation. In other words, when one is high, the other one's high, and when the other one's low, they tend to move around together. They're correlated. So if we only measure one of these, let's say we only measure x1, and we ask the question, well, what is the likely result or the likely value of x2? Even though we haven't measured it, well, what is its likely result? Well, we can intuitively, we would sort of, let's say, draw a line of best fit in our mind, or if we had an Excel or something, we get this line of best fit, and this is a least squares fit is what we would generally do. This is the same thing as fitting the first principal component to this data. Principal components is simply a least squares fit to the data. Then we project our point onto that line of best fit, or if we will, we project it onto the score space. And from there then, we can say, well, the likely result of our missing data is x2. And this process is called imputation, where we take the data that we've collected, we project it onto the score space, and then we see, based on where we estimate we are in the score space, then imputation is then to fill in all the missing values that are unknown. So the method that we use to get these forecasts is called imputation. There are many references in literature. I'll go through a few of these, and also one that I find very good, which is a comparison of many different types of imputation methods. But what imputation is just, if you want to think of it in a simple way, it's using our PLS or PCA score space model, treating it like a calibration curve of the process. And then based on the data that we've measured, we can then read off of a calibration curve what the missing data is. So again, in literature, and at the bottom there you see a very nice reference to a paper that compares different methods and does a comparison and explains quite well how these different methods work. I've highlighted a few of the most, let's say, common or important ones. The ones that are and I'll highlight the ones that are most interesting, but the steps in all of these are the same. our first challenge is, can we, from what we've measured, so we haven't measured all data, but from the data that we've collected, can we estimate what the score values are? And that's basically projecting the data that we know onto the score space and getting a good estimate of that score space. And there are different ways to do this. Once we've projected ourselves on the score space, then they all use the same method for then filling in the missing data. So it's just to take the model itself and use the loadings then to get the missing data. So again, if we take some of the most common methods in literature, iterative, or even in not just literature, but also used in commercial software, iterative imputation is generally the numerical way to solve, and that's you start off with an initial guess for the score space, and then you just keep iterating until you converge on a final value. You have projection to model plane, and this is where you numerically invert the model in order to project yourself onto the score space. The only challenge with this method is that that loadings vector there in the middle that you have to invert, that can become ill-conditioned depending on what data that you're missing. So this numerically sometimes has some issues. And it's been shown that iterative imputation does converge to projection to model plane, but iterative imputation has a little bit more stable numerical properties. So in software, it's usually done using iterative imputation. And then we have where we only invert each score one at a time. And then the problem with this is that with this method is that if you're, depending on what you're missing in your data, this can give, let's say, incorrect results if you're missing a large portion of the data or you're missing important parts of the data. So it's a little bit less stable. The benefit of the single component projection method, though, is that it's very simple. It's numerically, it's easy. There's no real inversions. It's just a single pass type of calculation. What we actually do in SIMCA-online is a little different. I'll explain that in a second. The actual imputation that's used in Control Advisor. But now if we say, using the data that we've collected up to the current time point, can we then use imputation to then forecast where the process is likely to go? That's what's happening then using that imputation method. Is we're taking these measured data, so the gray measurements there, and that's the data that's known. We're then using that to in a final BLM model to say, can we estimate the final BLM scores? And if we can estimate the final BLM scores, then we can use those and to infer or impute then what the missing data is or the future data is. So inside of Control Advisor, there's a method called imputation by regression, and it's an interesting method that shapes the score space in a slightly different way. And it's also single pass, so it's more computationally efficient than, let's say, something like iterative imputation. And if you're going to use an imputation method in an optimization algorithm, then if well, you need something that is streamlined and computationally efficient. So this method is both outperforms numerically in terms of predictive power, the common methods like iterative imputation, but it also is more efficient than iterative imputation. And I did a benchmark study, did a presentation at IFPAC a few years ago, benchmarking this method versus some other benchmarks. And what I found too is where it outperforms more prominently is as the process moves farther and farther away from a normal operation. So it's even more stable given a strange type of operation, which is even more important for inside of a control type of method. Okay, so moving on. Now, hopefully that gives a little taste for how it is that we use the data we've collected so far to forecast the future. And if we can predict, we can optimize. And here's a little picture of SIMCA-online showing two trajectories. One is if you do nothing, so if you run given the nominal recipe or just the regular recipe, and then the other is showing a trajectory of the what's called advised future. So if you are to take the results of the optimizer and implement those, then you get a more stable type of result. And what this then is called is model predictive control, where we use predictions of a future event inside of an optimization type of method to help us find the best future settings for our manipulated variables, or how should we adjust our recipe, or how should we adjust our process in order that the future of the process does what we want it to do. And the way that this works is, let's say we have a batch type process. Although I will say that even though all my examples here are batch, we also do support, and the same analogies can be used for continuous. The difference in a continuous type process is that it's a moving window that is used, but you still have history, and the history is used to predict the future. But then at a new time point, then it's like that whole matrix of data shifts with time. Whereas in a batch, the longer the batch goes, then the more of the known part of the batch is filled in. There's a fixed start and end time for batches. So the only difference between batch and continuous, well, there are many differences, but the primary difference from a data point of view is that in a batch, the longer the batch goes, the more and more of your data space is filled in. So if we look at this set of data here, we have our table of batch data in which we collect data for all of our variables that we're measuring. So pH, temperature, flows, DO, glucose, whatever it is. We measure those over time. So at some part in the process where I'm indicating now, we've collected all of the data up to that time point. So xk is to represent x known. These are measured values. And if we have BEM monitoring, so batch evolution models for monitoring, like I showed in the previous slides, then we can calculate the scores and DMOD X and hoteling and whatever else for those known values. And then we have the future up until the end of the batch. And I call this XD, that stands for the dependent X, so the future values that are unknown. So from in SIMCA-online or in SIMCA, then the XK, those are the data that are collected up to the current time point. Then we have the XD, these are the future values of the dependent variables. And they are found by imputation, like I just showed. Now if we have or in many processes, we have some ability to adjust things. And I call these XMV. So these are manipulated variables. That's a control, from control terminology. And what that means is, so for instance, we may control pH, which means that we measure pH and we also have a pH set point. So the pH set point would be the manipulated variable. You can specify the set point. That's not something you measure, it's something you can assign. And we may have a feed profile, we may have other types of things that we can, as part of our recipe or control system. So these future values are actually known. So in terms of imputing, even some of these future values are known, and they can participate in the imputation. So then what the goal is in optimization is to say, can we select the best set of those future manipulated variables so that my process does what I want it to do? And so how we do that is through the technical term, or the technical type of method we use is a sequential quadratic program. But basically what that does is you start off with the first guess. So the first guess is the recipe, the normal way that you're going to run the process. Then from that, you will then predict then what the future dependent variables are. So basically you use imputation, use all the data you've collected so far and plus these future XMVs to estimate then what the future trajectories are of your dependent variables. Then you evaluate the process. So what that means is you calculate your future batch evolution scores, your D mod X, your final batch scores in D mod X, and if you have any final Y predicted, like titer or some sort of end quality, you'll calculate all of these metrics, and then you'll evaluate how well you did. So what that means is that you'll have let's say a set point for some sort of quality metric. You'll have, let's say you want to maximize titer. So you put all of these different objectives in, or maybe it's that you want to, in the batch evolution, you want to follow a certain VCD profile, so cell density profile or something like this. And you can even put objectives like that into your controller objective. And then what that does is go into an overall penalty function, and maybe I'm getting a little bit technical here, but basically it says we have multiple objectives we're trying to accomplish, and then what the optimizer will do is find the best way to accomplish all of these simultaneously. And so it evaluates how well it did, how close it got to all of its objectives, and then it tries a new set of manipulated variables. And it iterates and sees, did that new set make the objective better or worse? And it does this in a way that it can use like a steep of, or a direction of steepest descent to go and find the global optima. Okay, so that's the way the optimizer works. Again, a very quick explanation, but if you want more details, you can always contact myself or anyone at Umetrics. So this type of model predictive control, if you go back to the processes that you're running now and think, how does this fit into an overall control architecture? So there are many different layers to control. You have, at the base, you have your regulatory controllers, and this is not like an FDA regulatory term. This is a control term. Regulatory just means you'll regulate something. You'll keep it in control. So you have your temperature controllers where it measures the temperature of the reactor and it adjusts like coolant flow, your pH, and it might adjust the amount of base that's added to a process, and your oxygen and other types of controllers. So they are simple type controllers living in the DCS, usually by PID type control or something like that. And then up top you have more supervisory type control that says what should the temperature be, what should the pH be, and so on. And so that's where this advised future, the model predictive control that's in SIMCA-online, that's where it fits in, is more in this supervisory type control. So it's not going to be making adjustments 10 times a second. It's going to be making more mid-course correction and more slower types of decisions that are based on final qualities or other types of quality type of decisions. And if you put words to what is the goal or the function of these two layers of control. Well, regulatory control, that's to give you consistency and process capability. Can you make the process do what you want it to do? Where supervisory control, its goal is more, now that we've got our process in control, we can steer it down a path that we consistently. Now the question is, what path should we take in order to get the quality we want, minimize or reduce costs or maximize yield, these types of things. So regulatory control keeps has a very small focus on the process, whereas supervisory control has more of a global role on quality and performance. And you can't be trying to do, or you'll have a challenge trying to do supervisory or model predictive type control if you do not have a good regulatory control layer. So that's a prerequisite. Now, putting this into context of the whole Sartorius environment, what I'm very excited of is, and this is now getting a little more specific into biologics, that we can fill all the bases under the Sartorius umbrella, where we have the AMBER systems to generate good data and build data sets that will make the right type of models that can do control, and we can have causal type of information in our data. And then we have, in the middle, we have our SIMCA environment where we can analyze the data and build all of our models and do all the modeling like I've just been speaking of, and assess, how effective are these predictive analytics? Does it look like we can forecast and do all of these types of studies? And then we have now much more options on the deployment side that, I'm speaking of the SIMCA-online and control advisor piece, but with all of the pieces from Sartorius now, we have a much more comprehensive ability to fill all the layers of control. And if I get a little more detailed into all the different layers of control, we can build nice, extremely complicated and messy slides like this, and I won't dwell on all the different pieces, but we can now fill all layers of control, where we have at the base, we have our regulatory control layer, and so we have partners and our own tools for doing this. So doing glucose feed and temperature and pH and all of these types of control. And then in the middle, we have our PAT layer, where we're using instrumentation like Raman or NIR or some other types of even just soft sensors in order to measure some, like for instance, an example would be that we use Raman to measure the glucose that's inside of a reactor. And then instead of just having a constant feed schedule, now what we do is we control the feed, we adjust the feed so that we get a constant glucose concentration inside the reactor. So that would be from the PAT layer. And then at the very top, we have now the model predictive control and the supervisory control layer to say, what should, now that we can control the glucose level inside the reactor, what should that glucose level be? What should the target be, so that at the end we maximize titer? And that's where this supervisory layer comes in. So again, just to summarize, with the now joining the Sartorius team, we can now, as a company, satisfy and deliver on all these three layers of control, which is very exciting. Now we move to a demonstration. So I will get out of PowerPoint and show SIMCA-online. So this is, I have on my PC, I have, let's say, a data simulator. It's called DB Maker. And what it does is it cycles through data so I can simulate a process that I have the data for, and that's what it's doing for me here. So this is a biological process. What we're showing here is a score in the top corner, top left corner. I have a score control chart, and we're watching this process as it runs. Actually, in my simulation, I have it set up to run parallel reactors. So we're actually seeing up to 3 run at the same time. So far, these two batches are running quite normally, so they're within our control limits, and we see the forecast looks quite good. Well, now we see this one, it looks like it's forecasting that some strange things may happen. So let's click. Now, so SIMCA-online is saying that it's likely that the osmolality, yeah, it's low. Our VCD tends to be a bit, oh yeah, it's low. And so we get both the measured and then the forecasted values as well. Down here, what I'm showing then is the titer. And what the data is for this is 1-day samples of metabolic type of measurements, so IPC type of measurements. And the nice thing that you see here, then, we can get what we expect the final titers to be, even though we're only partway through the run. Up in the top right, then I have a batch level score chart. And so you can see even before the batches are done, we see where we expect them to end up. And some strange things are happening. And I have both good runs and some strange runs in here to show how these two may look. And then down in the bottom right, I have then the final predictions of, well, actual predictions and measurements of the titer is what the one to the left is, and then VCD to the right. Okay, so this is an example of running the process in forecast mode. And then I have on another example over here, I have an example where we have it running in just monitoring mode. So here is what SIMCA-online looks like, and maybe what I can do is simplify the view so I only show what's running now on these two charts. So we have the process as it's running, then we have the forecast to say where does SIMCA-online expect the process to go based on how it's run so far. And then we have the advised future, which what it does, so we have here temperature as one of its variables that it can adjust. And so what it wants to do is lower the temperature. The recipe is right here like we see. Hopefully you can see my mouse. But what the advised future suggests is to lower the temperature during this phase of the process, and then later on you can see the temperature that SIMCA-online suggests as well. And what it's trying to do then is it's trying to maximize a final yield over here. So that's what its goal is. Now already though you can see this particular run that happens to be running during the demonstration tends to be one that's a little off. If we wanted to see why it's off, we can click, and we can also click on the forecast as well. So the level, someone opened up a valve or something and dumped some of the product, it looks like. Something like that. Okay, so that's a quick demonstration of the forecast mode and the control mode in SIMCA-online and how it looks. I'll go back to slides to wrap up. So these methods and Control Advisor, it's a module that runs inside of SIMCA-online. It's an extra module, let's say. but it's included as part of SIMCA-online if you have the license for it. We do offer, you know, if a half-hour quick seminar like this isn't quite enough, which I expect it's not, we offer courses, or we can do, well, if you're going to entertain Control Advisor, then there's much consulting that's offered as part of that as well. But we do train in the methods for education purposes as well. And I always like to point people to the YouTube channel for Umetrics. Since being acquired by Sartorius, we're still in the middle of rebranding many of the videos that are on there, but it's an excellent environment to go to for any reference, whether it be Control Advisor or other types of reference. In terms of upcoming webinars, we have some, we continually have these types of seminars, so I encourage you to go to the website and check those out. We have some future ones that are interesting coming up that you can check out as well. And just to summarize, so where this fits in is as part of the Umetrics suite. It's a pretty comprehensive suite of tools, right from design of experiment, which is to create data, all the way to then make prescriptive type of decisions based on analytical methods and modeling and all these interesting things that I've spoken of today in many different pieces. And then also, if you take in context of the Sartorius offerings as well, it's very comprehensive analytics and measurement and control and automation platform that we can deliver on. And so what these tools do, again, start from descriptive and diagnostic. So in other words, can we describe what happened and understand what happened and be able to diagnose issues? Move towards, can we predict issues before they happen? And then finally, once we get up to the Control Advisor piece, now we're getting prescriptive. We're saying that we've matured our models far enough that now we can have them help direct us to what changes should we make into the process to get a desired result. Okay, that's a summary for me. So maybe Leonard, you can open it up to questions.
Thank you very much, Chris, for this excellent presentation. I think if you go back just one slide before we open up, if you go to the prescriptive thing in the top left corner there, I think an equally important aspect is we can also find out how we should act to avoid a certain thing to happen, to avoid an hiccup or an issue. That is as important to understand how to act to accomplish a certain thing. We will very, very shortly be back to respond to all your questions. So for the moment, thank you for your time and attention.